Hello, calculus fans! Alright, so we're moving on to a whole new topic now. Our goal is to compute areas. Now, a lot of areas are pretty easy to calculate. So just as an example, we have several different ways of computing the area of a triangle. For instance, if you have a triangle of side lengths A, B, and C, and an angle theta between side lengths A and B, and then you have a height relative to side B as h, then there's a whole bunch of different formulas for the area of a triangle. Here, let's look at them. You've got 1/2 base times height. That's sort of the usual formula for the area of a triangle. You got 1/2 AB sine theta. That's actually a pretty common one. Here's one that you may not know, but it actually comes in handy every once in a while. It's Heron's formula, square root of s times s minus a times s minus b times s minus c. And s is the semiperimeter, where you take the perimeter and you divide by 2. Now, we're not going to use any of these right at the moment, but I just showed you this to point out that not only is it fairly easy to compute the area of a triangle, but there's lots of different ways of doing it. And it turns out we also have pretty nice formulas for the areas of squares, rectangles, parallelograms, trapezoids. And one of the things that all of these have in common, triangles and quadrilaterals, is they all have straight sides. They're polygons. And polygons are much more straightforward to compute the area of than things with curved sides. Now, we do have a couple of formulas for the areas of objects with curved sides. Circles and ellipses immediately come to mind. And I would actually say that's pretty much all we have in terms of basic area formulas. If you look for the formula of regions that have curved sides, you're probably not going to find any others. Now, I'd like to refer to some pictures in the book. If you look on page 332, figure 3 shows a parabola, and we're going to want to try to compute the area underneath that. Turns out that's actually really difficult to do. And with the techniques that we have up to this point, we actually have no way of computing that area. So instead, what we're going to do is try to estimate the area. Now, we're going to follow a procedure that the book discusses, and we'll create rectangles to estimate the area. Let's look at a picture. So what we're going to do is, since we want the area that's underneath the curve, we're going to break up the interval from 0 to 1 into 4 pieces, and then create rectangles over those 4 pieces. Those rectangles will go above the curve or maybe below the curve. A couple different ways of doing it. One of these is going to create an overestimate, one's going to create an underestimate. So we're creating rectangles to estimate the area. Rectangles, of course, are easy to calculate the area of. So in each case, we're going to divide up the interval 0 to 1 into what we'll call 4 equal-sized subintervals. So this is a new term that we have not used before. We're dividing an interval into subintervals, and then we're going to create rectangles above these subintervals. Now, in the first area estimate, the height of each rectangle is going to be chosen to be the height of the curve at the right endpoint of the subinterval. So let's just take this subinterval here. How do we make the corresponding rectangle? Well, the height of the rectangle is based upon the height of the curve at the right endpoint, which is 3/4. So we put 3/4 into the function to figure out how high we should go to make the rectangle. All right, now let's calculate the areas of the rectangles that we see in area estimate 1. Now, it's easy to see that the width of each rectangle is 1/4. And then we've got the heights of the rectangles going left to right. There's 1/4 squared, 1/2 squared, 3/4 squared, and 1 squared. And we get those numbers by plugging in these numbers, these what we'll call partition points, into the function to get the height. So we can write down an area now that we're getting in area estimate number 1. So we multiply the heights of all these rectangles by the width. So for instance, this term here, the 1/4 squared, is the height of the first rectangle, and then the 1/4 is the width of the rectangle. Now notice that all of the rectangles have the same width. They all have width 1/4. Okay, we're going to try to simplify this expression. First, we're going to factor out that 1/4, and this is going to be a common thing that we'll do with these. And then if we work through the calculation, then we end up with 15/32. If you want the decimal, that's 0.46875. Okay, so now we're going to deal with area estimate number 2. You might want to go back to the picture and take a look at the fact that the rectangles are going to be made so that the heights are found by plugging in the left endpoint of each subinterval into the original function. Okay, now the width of each rectangle is the same. The width is 1/4. But now the heights are different than what we had before. So the heights of the rectangles going from left to right are 0, 1/4 squared, 1/2 squared, and 3/4 squared. Now the height of 0 is because that there isn't really a rectangle above the first subinterval. If you go back and look at the picture for area estimate 2, there's really only 3 rectangles. In a sense, there are 4 rectangles, but the first rectangle has no height. All right, so now that we have these heights, we can write down an area for area estimate 2. That's going to look like this. Again, each term represents an area of a rectangle. So this thing that I've boxed here is the area of the first rectangle, well, the first actual rectangle. It has height 1/4 squared and width 1/4. And as before, they all have width 1/4 because we took an interval of length 1 and chopped it into 4 pieces. Okay, let's simplify this expression now. All right, so now we get something that looks like this. We get 7/32, and so we get our answer of 0.21875. That's going to be the area estimate that we get for area estimate 2. Now the book goes on and does a lot more calculations. You can check out what they're doing. They actually choose more rectangles. And then the picture that you see that's on page 333, it makes it plausible that the more rectangles you choose, the better the estimates are going to be. So as you choose more and more rectangles, what you should be able to see is that the area under the rectangles is very close to the area under the curve. And the more rectangles we pick, the closer we're going to get to the actual area. Okay, that's all for now.